Welcome to EET3329C Communication Systems at Valencia College for the fall semester of 2020. This is your lecturer, Dr. Wilfredo Rivas Torres. Lecture 4 is going to be divided in two parts. This is part 1 of Lecture 4. And for Lecture 4, we will be talking about analog modulation and demodulation. We'll talk about the topics for today's lecture is carrier communication. We'll talk about double sideband and single sideband modulations. We'll talk about the local carrier synchronization concept and some frequency division multiplexing. So carrier modulations, right? So in terms of analog modulation, any of the basic parameters of your carrier, you can make it vary linearly with your information signal. So that parameter will carry your information, right? And depending on which parameter you're changing, you end up with either amplitude, frequency, or phase modulation. Now, AM is known as a linear modulation, while FM and PM, which are closely related to each other, they have lots of similarities, are nonlinear. And you'll often hear in the trade talking about FM and PM as angle modulation. Now, communications that use modulation to shift the frequency spectrum of your information signal is what we know as carrier communication. So modulations, we've been calling our baseband signal M of T, and M we use it because if you remember when we started the course, we always were talking about message, and that's still the same concept, except that every once in a while I call it baseband signal, right? And if you have an M of T, we also denote the Fourier transform of M of T as M of F. So M of F would be the Fourier transform of M of T as we have discussed frequency in this course. Now, the Fourier transform actually revealed earlier on a very strong property that we will use, right? It's called the frequency shifting property, and we discussed this property at length in lecture number 3. Recall that the shift of the frequency response of MIT to a new frequency band, center F of C allows us to match. We're doing this because we want to match our signal to the channel, right? So if we know that in order to transmit our signal through a certain channel, we need to be at a certain frequency. And there's many reasons for that, right? One of them being like in the U.S. Regulatory Commission is the FCC. They tell you what frequency you have to be at. So in other words, what we will do is we multiply M of T by a sinusoid at the frequency f of C, and it takes on this form, right? So here's a message signal times cosine of 2 pi f of t, right? Now, notice that M of T is taking on the position, and normally that's where we put the amplitude, right, of the cosine. And then you will see as a cosine of 2 pi ft. Now, the aim of a carrier modulation is to move the signal content, the information, to be centered somewhere around f of c, which is your carrier frequency, right? So for s of 1 of t that we just saw, you end up with a Fourier transform that takes on this form, right? And again, this is the frequency shifting property of the Fourier transform, right? It's totally defined by this, and it's the property that we're using here. So this simple multiplication is in fact allowing us to change the amplitude of a sinusoid to be proportional to the message. And this is what we know as amplitude modulation, or AM. Um, More broadly, we can express our signal in much broader terms, right? We can have S of T have A of t, an amplitude that varies with time, and even a phase that varies with time. All right. Now there's three variables. Notice that we're not showing frequency as a variable of time. And that'll come when we start talking about angle modulations, that'll become more obvious why we didn't do that here, right? But any of these three things can change, either the amplitude, the frequency, or the phase, right? And then indeed, the message signal can be used to modulate any of these three parameters, right? And we would call an amplitude A of t, that's a linear function of the message. That's what we call amplitude modulation. The same thing with frequency and phase modulation. Now let's talk. AM comes in um, several distinct types. Okay, and we're going to start off with double sideband amplitude modulation. Okay, um, just because it's the easiest one. All right, and that's where we're going to start. Um, so amplitude modulation again is because it's characterized by the formation bearing carrier amplitude is again linear with a linear function of the baseband message, right? Now we are going to make the assumption, or we're going to fix our carrier frequency to f of c or omega c, right? If we put in radians per second. And our phase of phi of t, we're actually going to make it a constant. Actually, in most cases and in most of the mathematical derivations that we're going to do for AM, we're going to assume that the phase is zero, and that's without any loss of generality, right? It's a constant. The phase here is a constant. We're not going to change the phase, okay? So might as well assume it's zero. Um, so we're going to have a modulated signal that's going to take on this form, m of t cosine omega ct, right? And as we saw earlier, if we have an m of t and we know what the Fourier transform of that is, then all we have to do is just uh, shift in phase our m of c, right? Remember we talked about these shifting properties when we talked about special functions. That was in lecture number 2. So this is the same sort of concept, but in the frequency domain, right? And you have a positive shift and a negative shift. Okay, so diving into the details of double sideband AM, or double sideband amplitude modulation. Um, Notice that you are going to shift M of C both to the right and to the left. So you start off, let's say, with a signal M of T that, let's say, takes this shape and has a Fourier transform or a frequency response that looks like this, right? So B of this figure shows that the relationship between time and frequency domain. Now, when you modulate the signal, and you AM modulate it as a double sideband signal, what happens is you are going to take this response, right? And remember, we look at the response around zero, but really our signal, what we're really interested in is what happens in 0 and above, right? The reason we show it like this, as I explained before, is that this is mathematically correct. So the mathematics make us do this, right? When you do the Fourier transform, you end up with this thing that has the same signal mirrored on the negative side, okay? Now, when you go ahead and modulate it, what ends up, you end up with a signal that gets shifted both to the left and the right, right? The spectrum gets shifted to the left and the right. And the amplitude, by the way, drops by half. So this used to be 2A in magnitude. Now it's simply A. Okay? Um, there's one more curious thing, and it's a little bit hard to see in this figure, but unless there's a real DC component here, you do not end up with anything. You do not end up with a carrier, or there's no value or no component at the carrier. We'll see an example in a little while here, right? Um, and for this reason, right, double sideband is actually known as double sideband suppressed carrier. So the carrier information is not sent, or you do not get the carrier information. Okay, it's it feels kind of strange, but that's kind of what's happening. The carrier is really not included unless you have some really strong value at DC, which this kind of shows a strong value at DC. But in in real terms, that is not a requirement for a signal to be baseband. Right now, we also before I keep going, we also talk about. Um, I think it's coming in a little bit. Let me hold on. If it's coming up in a little bit here. So in order for us to recover the signal, let me continue with my slides here. Uh, it is we also are going to have to take these spectrums and retranslate them back to baseband, right? Because that's really where our information is. Our information is a baseband signal, right? So that process of recuperating your signal, your information, excuse me, from your carrier signal or your modulated signal is what we call demodulation. Okay. Now observe that when we do that, that's here in part D in this figure. Um, what we actually do here is we multiply the signal again by the carrier. And when you do that, you end up with a spectrum that looks like this. And if you carefully look at the Fourier transform, which we're going to do in a little bit, you kind of understand what's going on here, right? So you end up with something that, again, kind of looks similar to what we had in the beginning. And you end up with these two um, uh, frequency components, right, that are 2 times your carrier frequency. Okay. And how did that happen, right? So what happens is when you multiply your carrier, which is mt cosine omega ct, by cosine omega ct. So what we're saying is that on the receiver, before we demodulate the signal, we need to know we need to have a copy of the carrier, right? So we need to generate that signal. Now, when you multiply them together, you end up with a signal that would be this EFT, right? So represented in the figure by this, right before this low pass filter, right? And if you do some trigonometry identity of cosine square, which is 1 plus cosine of 2a, if you kind of guys remember that, you end up with an expression that looks like this one. And this is what resulted in that 2 times f of c right here, right? So that's what's responsible for these two components. Right? And then you have M of T, which is the one in the middle, which is the one that we're actually interested in, right? So um, here's the way to look at it in the Fourier transform sense, right? You end up with, again, M of F, and then those two components, which are 2FC and minus 2FC, okay? Now, how do I recuperate my information? Well, I put it through a low-pass filter that should get rid of the two, right? You kind of see a little shadow of the low-pass filter here, okay? And it should let through the baseband signal, but eliminate the two times the carrier frequency signals that are present, right? Those would be eliminated. So at the output here, you have half of M of T, okay? Now, this is a method that's quite interesting. It's called a synchronous detection or coherent detection. Okay, uh, synchronous detection or coherent detection. What that means is that the receiver would need to generate a carrier that has the same frequency and phase. So it has to stay phased aligned with the incoming signal. And this is what we call phase coherence, right? So they have to stay synchronized. Okay. Um, okay. So let's go to an example. So let's say we have a baseband signal, some kind of cosine waveform. We know that the cosine has this sort of um, Fourier transform, right? Plus or minus FM. You're going to half of the amplitude. And we want to sketch double sideband suppressed carrier, right? And what we do is we just take these two and we shift them by f of c, right? So if you take this one and this one and shift by f of c, you have to reduce the magnitude by half. So this was already 1/2, so it reduces to 1/4. And you see there's no DC at this point, so there's no carrier here, right? See, there's no carrier. That's what we meant by suppressed carrier. And the same thing happens to the one that shifts to the left. There's no carrier. And now you can see why we call this the upper sideband, and this is the lower sideband. So anything above f of c is what we consider the upper sideband, and anything below the lower sideband. On the negative side, it's kind of the other way around. Um, but remember, we normally don't speak of this in actuality, right? Again, this is that mathematical thing that we were talking about. Now, if we go to demodulate this signal, right, we should end up again with this being shifted back down to baseband. Okay, so here's our modulated signal, gets shifted to baseband, and then it gets spread out another FC, so it ends up around 2 FC. Again, the magnitudes of these get reduced by 1/2, but we don't really worry about these two because we know that we're going to have a low pass filter, and we're going to get, and they are going to get filtered out. Okay. Um, this is one of those things that's fairly straightforward to do in MATLAB or Octave. So why don't we go ahead and take a shot and look at it inside of Octave. Okay, so we're here in Octave. Um, and I have a script for those of you in the class. I will post this. Um, uh, the usual, right? We define the carrier frequency. Um, I'm going to do a single tone like the sample that we just looked at. I'm going to use 5,000 hertz or 5 kilohertz. I'm going to use a carrier of 1E6, which is 1 megahertz. I'm going to set the sampling time to 1 over 4 times the carrier frequency. Again, I could have just set it to 1 over 2 and still satisfy the Nyquist sampling criteria that we've talked about. But I decided to use 4. So going a little twice beyond normal Nyquist. The rest of the things should be kind of familiar to you right now. I am going to run this for a total of 100 cycles of my modulating signal. So if you know what the period of that is, multiply it by 100, and that's what the total simulation time. Here's where I'm defining it as a cosine. That's our message signal, if you will. Excuse me. I am going to do, again, a few calculations. So I calculate the resolution bandwidth, which is 1 over the total simulation time, right? Here is the Fourier transform. So this is M of F. And the rest of it is pretty much plotting. Now, I did something a little bit different this time. I actually calculated the signal power, and I'm going to show you guys the signal power. And the reason for that, remember, I mentioned, and I went a little bit out of my way to tell you guys that when you modulate the signal drops by half. Now, that's in voltage. Whenever you drop the voltage, right, and we're going to look at that in dB. So if you remember the dB, the whole thing about dBs is you would do 20 log of 1/2, which is minus 6 dB. And we should see that, right, when we run this. And you guys can kind of see that what I'm leading up to. And in fact, that's what we get. And then here on line 41, this is our double sideband suppressed carrier signal. Notice I just multiply M of t by the cosine of 2 pi f of c. Okay, and then the rest of it is just the Fourier transform and then some more plots. Okay, let's go ahead and run this. All right, let me bring this into view for you guys. Okay, try to make it a little bit big here so we can sort of talk about it. All right, so I didn't plot the whole 100 cycles, of course not. I just plotted two of them. And so this is our message signal here in the upper left. In the upper right, that's the AM modulated signal, right? Notice that the amplitude follows our modulation signal. Now, you can't see the carrier because the carrier is moving so fast, right? But what if I did want to see it? That is the question. So let's go back, right? So if I, instead of making this 1 megahertz, let's say I made it 100 kilohertz. Let's see if that's enough. And sure enough, that's enough. Notice that now you can see the carrier, right? And it's clearly seen, um, and I have proven to you guys that the reason you couldn't see it before is because it's going so fast compared. The carrier is going so fast compared to the baseband signal. Now let's go back to our original carrier. Okay. All right. You'll notice here is on the bottom left is the message signal Fourier transform. Now this P power equals 24 dBm. That is the power of either of these peaks, right? There's two peaks that are identical. We know that. And they're 24 dBm, right? If you calculate how much is 1 volt into 1 ohm in power, you'll see that that is actually 30 dBm, and it drops by 6, which is the 1/2 factor that we've been talking about. We get 24. You guys should go ahead and convince yourselves about that, okay? Um, the only thing is, when you calculate power, remember to take into consideration the resolution bandwidth, which in my code it does. And I'll let you guys look at how we do that. Okay. Um, Now, when we modulate it, we know that the signal should drop again half, and that's another 6 dB. And here on the bottom right-hand side is the Fourier transform of our modulated signal. And notice how these two are shifted by 5 kilohertz from the carrier, which got the carrier is at 1 megahertz, which we expected. And again, the peak power here is 18, which is again 6 dB less than what we saw on for the message signal alone. Again, confirming what the theory says, that it should be half, right? Notice no carrier. There's no signal here at the carrier, which is at 1 megahertz or 1 E6. Okay. So let me go ahead and pause here and go back to the slides. All right, so we just were talking about uh, double sideband suppressed carrier, and we already mentioned that it requires coherent demodulation. So at the receiver, you need to again have a local copy of the carrier, and it has to be coherent on synchronization with the carrier of the modulated signal. Now, in practice, that is not easy to do. Keeping those two in synchronization is rather difficult, especially the farther away the receiver is from the transmitter. Right. And after a certain distance, it doesn't matter anymore. It's just going to be hard. Right. The other thing that can happen is, right, the receiver can have a certain movement. Now, whenever you have something in movement and you're trying to get a signal to it, or you're transmitting a signal from it, you get something that's called the Doppler shift, which is that the parent frequency of your carrier seems to change, and it's all due to movement, right? And this was actually predicted by Einstein, right? This is this famous train station experiment in special relativity leads to this Doppler effect, even though we knew about Doppler effect even before that, even before Einstein, I mean. Okay, but without going too deep into the details, what happens is your receive signal, let's call it RFT, you're going to have a certain delay because of the distance. We know about this. We talked about it before. And you're also going to have a change in frequency. So not only do you have a time delay or a phase difference, right? You are also going to have a change in frequency. right? And this makes trying to generate a coherent signal at your receiver that much more difficult, right? So wouldn't it be nice if we had something that didn't need this requirement? Okay, and that's amplitude modulation, by the way. Notice that I'm saying AM, no suppressed carrier, no double sideband, none of that stuff, just pure AM, right? So the alternative to not having to have a coherent demodulation process is for the transmitter to actually send a carrier. Come on. Yeah, you know what the carrier is, right? Just because I didn't put something at DC, you're not going to send me the carrier? Come on, right? So if we could come up with a way to do that, and not depend on the kindness of the transmitter, we could avoid this requirement. And there is such a thing, right? So what we do is we want to have an AM signal that looks as A cosine omega C. Here's the carrier by itself plus the modulated carrier. If we could do this, which means, right, cosine omega CT is the same for both of these, so we can take it out, and you end up with something that says A plus MT cos times the carrier, right? So essentially what we're doing is um, we're still kind of sending the double sideband suppressed carrier, because if you look at the Fourier transform of what I just showed you in this equation, which is down here, right? If you look at the Fourier transform, the first half is the same thing, but then you have the two, oh, well, this one should have been a minus. I'm sorry for my typo. Um, let me see if I can actually today. Um, um, so today I'm going to try to use my pen. So this is wrong. It should have been minus. Okay. Um, So you're going to get the two impulses, one at plus and one at minus FC, right? And which is what the carrier should look like, right? So remember, the two signals are pretty much identical, except for the amplitude is, instead of being just MT, it's going to be A plus MT. And we always choose A to be a positive number or something greater than 0. And we'll look into more restrictions of A in just a little bit. So we're going to use this figure to talk about A, all right? So there's two cases, right, worth talking about. The case where A plus MT is greater than 0 for all t. I mean, this term, okay, this term would always be positive, or when our term is always less than 0 or negative, right? So if this were our information signal, this is the one, what we need to do is DC shift it, right? Because this line through here is 0. We should apply some kind of DC shift such that the signal is always positive. See here in this case, the signal is always positive, never crosses 0. However, in this case, we can still put an A, but it wasn't enough, and then the signal is still negative in some portion of the signal. Right, so those are the two cases we're going to look at. In the first case, right, when we modulate the carrier, which is down here, right, at the bottom left, you'll notice that the envelope, so here's the carrier, and the envelope of the signal, right, the envelope of the modulated signal will track or be equal to our information or message signal, okay? That means that as long as we detect, all we have to do is detect the envelope. And if we can detect the envelope of this signal, right, we can recuperate our message signal. So what we're saying is that as long as A plus MT is greater than 0 for all t, we can recuperate our signal from the envelope of the AM modulated signal. Okay. So the real condition says there's another condition that hardly anybody ever talks about. So Condition number one actually says that the carrier frequency should be much, much greater than the bandwidth of the message signal. That is a requirement, okay? If you don't meet this requirement, you're not translating it far enough uh, in frequency, and you just might have some other kinds of distortion because you're wrapping around zero or something of that nature when you look at the Fourier transform, right? Um, and then there's a condition that we were just talking about, A plus MT must be greater or equal to zero. Now, if you ever had a double sideband, right, where M of t is greater than zero for all t, then you already satisfy condition number two, and you're done, right? There's no need. Even A would be, you can leave A equal to zero and you're still satisfy it. So double sideband suppressed carrier, right? As long as everything is greater than zero, right? The whole information signal is greater than zero, you're fine, right? You don't have to do anything special. And actually, at that point, you really can't tell it apart from AM, right? Okay. Um, Now, for the case where, um, where is that? Okay, I'll just talk to it. So in the case when you cross zero, what ends up happening is when you look at the modulation, notice what the envelope looks like now. See, the envelope goes for a period, for a portion of the time, it does look like our signal, but then it doesn't, right? Because our signal always keeps, after the peak, is monotonically decreasing all the time. But notice here that all of a sudden it starts to increase. So this would be a distortion for us, okay? And that is explained somewhere. If not, I'll go back to the slide and make sure that um, we explain. Oh, I think it might, never mind. Let's talk about amplitude modulation. So let's say that we have a signal with a peak value, we call it M of P, right? So our signal goes between plus or minus M of P. Those are our peak values, plus and minus MP, right? Um, and that's what this condition here is talking about. And condition number two in the prior slide means that whatever the minimum is, right, A has to be greater than that minimum. So whatever you're going to shift the signal, DC shift your signal, it has to be greater than the negative of the minimum. So if this minimum in this signal is minus MP, I am going to have to shift this whole signal at least by MP, greater or equal to MP. That's what it's saying. Okay. Um, we also define what's known as the modulation index, and we use the Greek letter mu for that. And that is whatever the peak value is over A, right? That is called the modulation index. So if you make A equal to minus MP exactly, then you have a modulation index of 1, right? If you make A any greater than MP, then you have something that's less than 1. But it should never be negative, and in the limit, it can go down to 0, even though 0 means that your signal originally already was equal to 0 or greater. So what that means is mu cannot be less than 0 or greater than 1, right? So it has to be somewhere in between, okay? So here's an example, and what we're going to do is we're going to sketch the signal for a modulation index of 0.5 and for a modulation index of 1, okay? When our message signal is B cosine omega mt, okay? Um, so in this case, the maximum or MP plus is B, and the minimum is minus B, right? Because we just have a cosine signal, right? That's the two peak values. Therefore, we know that our modulation index is always going to be B over A, right? In this special case. So as a result, you can end up with an equation that looks something like this, right? B um, equals mu A, so we replace B with mu A, and then you end up with a signal that looks something like this, right? So that's your information signal. Um, the authors like to explain it with the actual modulation signal, and this is all correct. Let me show you guys what I think it's a little bit uh, more direct and sort of helps you guys understand a little bit better what this mu thing is doing, right? So when talking about the envelope, look only at the positive side of the modulated signal, okay? So this is the correct modulated signal for mu equal zero point 0.5, right? But if I show you this, if I just give you this equation and say zero point 0.5, right? So you know that this is 1 plus zero point 0.5, that's what this value here should be, right? And then when cosine, that's what cosine of this is 1. When cosine of this whole thing is minus 1, that's what this value should be. So you're going to have 1, and if mu is 0.5, 1 minus zero point 0.5, then that's zero point 0.5 down here, okay? Now notice that the author did everything in terms of A. So note that MP is the envelope, peak to peak divided by 2, or just the envelope peak, right? So, but when I say envelope, I'm talking about the envelope of the modulated signal, right? But only, I already told you guys, only on the positive side. Don't look at the negative side. So it's not this peak to peak, right? It's the envelope peak to peak. So this peak and this peak is the one that we're talking about, right? And by the way, the value A that they're talking about is actually the average of this envelope, right? Or the DC, you can almost think of it as a DC value, but it's not totally true to think of it about it that way. Okay, at the carrier level, at the you're talking about the message signal, sure. Okay, so it is a DC value at the message signal. So it's this average value between the two peaks. Okay, so what we end up doing if you kind of follow this, right? The peak to peak value here, right, is A1 half and A1 half. So the peak to value, the peak to peak divided by 2 is A divided by 2, right? And then we know that the mean value, because they're telling us right here, is A. So when you divide that, this is where you get the 1 half, right? And that comes to 1 half. The same thing happens with U2. If you look at this peak to peak, it's actually 2A, right? So if I take 2A divided by 2, what's the average value between those two? Well, it'll be A. And I divide it by A, and I have a mu of 1. That's where mu of 1 comes in. Okay, so I could ask you in a problem to sketch these, or I can give you these values and voltages, and you guys can tell me what the modulation index is. Right, so those are the typical problems that one sees when talking about modulation index and AM signals. All right. So what I'm going to go and do now is, and I promised you guys at the beginning of the course that we not going to do a lot with circuits, and we're still not going to do a lot with circuits. So I'm not going to ask you to analyze, for those taking the course, to analyze any of these circuits or build them in the labs or anything like that. But to be complete, it's good to have a reference, and hopefully most of these circuits you guys have seen before. Okay. Again, the purpose here is just for a complete view and to be sort of thorough in our discussion. Okay. Now, the author of our textbook also discusses this, and they go into a lot of the details. And for the sake of time, I'm not going to do that. What I want to do is stay at still a little bit higher level. Right. Sorry if some of you think I'm doing too much hand waving. Right, but I did borrow this following slide from 22 to 35 from textbook called Principles of Electronic Communication Systems by Louise E. Francel, the fourth edition. Okay. Now we're going to talk about amplitude modulators or AM modulators. So diodes and transistors do not have a pure square law function, right? They're not square law in terms of the voltage and current relationship, right? So what that means is that you end up producing things like third, fourth order, and higher harmonics, right? We like to lump all of these and call them intermodulation products. Typically, depending on the conditions, and most conditions this is true, intermodulation products are easy to filter out, like we saw with the 2FC when we're talking about double sideband suppressed carrier, right? So tuned filter circuits filter out the modulating signal and carrier harmonics, leaving only the carrier and sidebands that we are interested in. Okay, so the message signal should not get through this circuit, right? The harmonics should not get through this circuit. Only the carrier with the modulated carrier, I should say, get through. Right, and you can think about this. Let's say we have a diode and we put our modulating signal and our carrier in a certain way so that they add together and end up at the input of our diode. This is not a practical circuit. We'll see a little bit more practical circuits in a minute. This is just for visualization, so you guys kind of see what the concept is. So if I put this addition of these two through a diode, right? Diode is a nonlinear device. You end up with all of these spectral components, right? So here's the modulation signal. You do end up with harmonics of the modulating signal, right? That's our information is. So you do end up with those. You do end up with your AM wave, right? Here's the AM wave, and then your two uh, lower and upper sideband carriers, right? So this is all your AM. This is what we want. And then you end up with harmonics and other products that you don't want, right? So we would normally just filter this out. Um, how would you kind of filter that out? Well, here's a possibility. We can put a resonant frequency, an LC tank circuit, right? So notice that at low frequency, the inductor looks like a short, so any low frequency would be shorted through this path, right? Because the capacitor will look like an open to that one. Um, we want this to represent a really high impedance at the frequency that we are interested, our AM modulated waveform, so it looks like an open, so they have nowhere else to go but to the output. And then at higher frequencies, the inductor looks like an open, but now the capacitor looks like a short, so those higher frequencies get shorted to ground. And there you go. That's how you end up with your AM signal. Okay. Now, in practice, there's two kinds of modulators. This author calls them low-level and high-level modulators, right? So in a low-level modulator, we create the modulation at small signals. So typically, when you have a transmitter with all kinds of blocks and things, and amplifiers and filters and other things that go there, uh, you would modulate it in the first circuits and stuff where the signals are still relatively small amplitudes before you start amplifying them. And the last stage of any transmitter usually is a high power amplifier. And that's usually the last stage before the antenna. Um, and for a high level modulator, you would actually modulate the signal there at the high power uh, final amplifier stage. And we'll look at that briefly. All of this, we're going to just, again, look at it sort of briefly. So here's a little bit of a practical circuit, right? Notice that we created sort of an adder. This adder could be something, um, some other form of addition. Here's probably the most simplest one, which is just these three resistors make up your adder, right? And you could tell with um, voltage division, that was the word I was looking for. With voltage division, what these voltages would be, how much each one, the carrier and the modulated signal, will contribute to this point. They add up. go to the nonlinear device, and we already talked about how this tank circuit would work, right? You could also use transistors. You're not limited uh, to diodes, right? As long as you have the resistive mixing network would work and the LC tune circuit. Um, Remember that in a transistor, the emitter base junction serves as a diode, and therefore there's your nonlinear device. So the modulation and amplification, right? So you, it can still work as an amplifier. You can still have gain, right? Occurs as the base current controls a larger collector current, right? So, and the LC tune circuit here rings to generate the missing half of the cycle. Okay, that's kind of the way that one works. And this is what it looks like, right? Notice that we use a BJT because we're kind of making the reference back to the diode, but this can be other types like FET transistors, for example, right? You can still do that, right? And this would be your AM signal. Um, Notice that in this one we show part of the bias, right? There might be some other biasing for the base and stuff that we're actually not showing. Um, there is also differential amplifiers that we can use as modulators, right? Um, and again, you have some good gain and good linearity that comes out of it, and you can actually have 100% modulation, right? When you need that. Remember that the modulation index, if you put it in percentage, it will go between 0 and 100, right? You can have up to 100%. The output voltage can be taken from the two collectors of the balance, or you're going to have a single-ended output. And the single-ended output is probably the more popular thing out there. Um, Even though nowadays with so much integration, I think most folks are using differential outputs as well. Okay. The thing here is we're going to apply it to the constant current source. That's where we're going to apply the modulating signal. Sometimes we call that the tail current. Um, the modulating signal is going to then vary the emitter current and therefore the gain of the circuit. And this results in an AM output. So essentially, we're using the modulating signal to change the bias current, right? So here's what the differential amplifier normally looks like. And here's the one with the modulation. Notice that the modulation is coming in at the base of the tail um, bias transistor, right? And this is the one that sets the current for the differential amplifier, right? So if it's varying with the modulating signal, that means that the current through these transistors also varying, and that varying of the current, right? If you look at the gain formula that we have written down here, you guys probably can't see that from this picture, but it says RC times IE, and IE is the one that's being controlled by our modulating signal, divided by 50. Um, and, and, and so as this carrier signal is going in, it's getting amplified by this circuit, right? The differential circuit, because the current is going up and down. Guess what? The signal at the output, right? At this node here, at this collector for Q2, is also going up and down as a modulating signal, right? The message signal, right? And that produces our AM signal here. Let's talk about high level. In high level, the modulator varies the final RF stage. Sometimes we call that the high power amplifier. It's the very last thing in the transmitter. And this can result in some high efficiency RF amplifier and transmitter, okay? Normally, we like to use some linear amplifier, so something like a Class C. Um, and then what we do is we apply the modulating signal such that, again, it varies the bias. You'll see it in a minute. And we somehow have to couple to the antenna, and we're going to show it through a transformer. So this is the idea behind it. Notice that BCC for this transistor is down here. And again, we're going to couple into it with, in this case, we're showing a transformer. And we're going to have probably some amplifier to amplifier modulating signal so that we can vary, right? The current going into the transistor. And again, we get that effect where the gain is going up and down. And we somehow have to couple into the antenna. Again, they're showing it here with a transformer, right? There's different ways to do that coupling, but right now, transformer is kind of the most logical and kind of easy to understand. All right, so that's as much as I wanted to say about circuits. So let's get to the concept of demodulating AM signals. Um, so, like as we said, we need a coherent local carrier to be able to demodulate the double sideband suppressed carrier signal. So we could use that with a regular AM signal, but that sort of defeats the whole purpose of doing AM in the first case, right? So in the case where we have mu less than 1, the envelope of the AM signal follows the message signal M of T. By the way, you can have mu greater than 1, it's just that you're going to distort your signal, right? So typically if you solve a problem and you solve it and you end up with mu greater than 1, you know you have a problem. Uh, so we're going to describe two non-coherent methods for AM demodulation. We're going to talk about a rectifier detection and an envelope detection. And would you know it, we were talking about modulating with diodes, and now we're going to talk about demodulating with diodes. It's one of the nice things about AM, and I think part of it goes back to the fact that AM is linear. You modulate and you demodulate it with similar circuits. Okay, so if an AM signal is applied to a diode and a resistor circuit, right? Diode and a resistor circuit, like in this case here in the figure, the output across the resistor is going to be a halfway rectified version of the AM. So here's the AM signal that comes in, and after the diode, you just have the upper side, right? The positive side of the signal. Same way a rectifier works, okay? So it's like cutting off the negative half cycle of your signal, right? Um, so you can do a little bit of the math behind it, right? The halfway rectifier output in node 1 ends up being VR, right? This is VR at node 1 after the diode. Ends up being something that looks similar to this, right? Um, and you're going to multiply it by this WT, which is something that only keeps the positive side, right? And you can do this sort of series extension of what WT looks like, or what your rectified waveform looks like. And there's theories behind it, no need to get into that. But you end up something that looks like this, right? Very similar to one of those Fourier series that we were talking about, right? Then that's pretty much what it is. Um, so you notice from here that you're going to end up with your signal plus a whole bunch of stuff that's higher in frequency. It's going to be the carrier or higher, right? So it's going to be harmonics of the carrier. And in this case, they're showing all the odd harmonics of the carrier, et cetera, right? So we would put a low pass filter, right? And if you put a low pass filter, you end up with 1 over pi A plus MT, which is really close to being your signal. Now, if you put a capacitor, which makes it AC coupled, I mean, which means you get rid of the DC, which in this case is this A over pi, you end up with VR being 1 over pi times MT. So this is your message signal within a multiplicative constant, which we can remove that constant by just putting some gain, right? Okay, and that is pretty much the way a rectifier demodulator works. We also have an envelope detector. The envelope detector still uses a diode, right? And but the idea here is you want to put a capacitor, an RC circuit after it, right? A parallel RC circuit. And you guys can certainly read here how it works. But the idea is you're going to put an RC circuit such that as the signal increases, so does the voltage across the capacitor. Once the voltage begins to drop, the capacitor right? This diode becomes reverse biased to begin with because the capacitor is going to be at a higher voltage, but then the capacitor is going to begin to discharge through the resistor. The trick here is, right, that you have a discharge that is slow enough so that it follows the envelope. Notice that right now you end up with this thing as they're showing it, and this something that looks like a little sawtooth, right? Well, um, or or we can call it a ripple, right? Now you can reduce this ripple choosing a larger time constant. That's the product between R and C. Um, so that the capacitor charges very little between the positive peaks. So RC should be greater than 1 over omega C, right, which is your carrier frequency. However, you cannot make it too large because if you make it too large, what happens is then the capacitor doesn't discharge or discharge very slowly. And then what happens is, again, you introduce a distortion. So there is sort of a trade-off between how closely you can follow and how closely not, right? Before you start to actually create more problems than you're solving, right? So quite honestly, what the rule is, you want 2 pi times b, which is b is the bandwidth of your signal, to be less than 1 over RCs, and that's kind of how you select RC. And always make sure that all that is much less lower than FFC, which is a condition for AM modulation that we explained a little while ago. Okay, and you know what? If this produces too much trouble for you, or if you have some kind of a DC term, you could put a high pass filter. And if the ripple is causing you any heartbreak or trouble, you can actually go ahead and put another low pass filter after that, and you will get rid of the ripple that because you can see the ripple is a sort of has a high frequency content to it. All right, now in the book in section 4.4, this is where the author talks about single sideband and vestigial sideband. Now the concept behind single sideband, remember when we were looking at uh, double sideband suppressed carrier, that we have a lower and a upper sideband. So there's one of these efficient amplitude modulations called single sideband. So the idea is you come up with a technique where you get rid of either the lower or the higher sideband because you don't need both. You actually, when you send both sidebands, you're actually sending double the information, right? If you go back, it's like saying I don't need to send the two sides of the IM signal, if you will. So just send one and you're good. Um, we might talk. I think we're going to talk more about single sideband when we talk about digital signals. So I'm going to hold on for that maybe for a little bit later. Now for vestigial sideband, um, contrary to single sideband it really aims to be perfect. Just get rid of one of the sidebands, right? Now vestigial sideband is much simpler, right? Less complexity, but it doesn't do a perfect job. So you still have maybe somewhere around 25% of the other sideband that you don't want. Um, but that is still better than sending the whole thing, right? You don't have to send the whole bandwidth. And when you think about how crowded things are, the TO sideband lets you put more stuff, and especially when you're doing FDM, frequency division multiplexing, right? Um, Now, I don't feel bad not talking about vestigial sideband because the only place that I'm aware that they ever used it was in analog television. And analog television is all that stuff has gone to digital, so we really don't really worry about that anymore. Um, and again, I can't think of any application where we use it. So that one I'm just actually going to drop altogether. And again, we might talk. I'm pretty sure we're going to talk about single sideband later on in the course. And I'll come back to it. All right, so that's all for today's lecture. Next time we will talk about nonlinear modulation or angular modulation, generating FM waveforms, the demodulation, and then we'll talk briefly about super heterodyne AM and FM receivers. Until next time.